Welcome back to Math 104. We are studying a game in which you roll a four-sided die, and whatever number appears on the die, when you roll, you receive twice that number of dollars as the payoff. The question is, in the long run, what will your average payoff be per play of the game? Now, we could look at very large numbers of results of these die rolls and their associated payoffs and compute the average. For example, I've here set up my Excel spreadsheet to carry out large numbers of plays of the game and average the results. Here is the average. And I can keep playing again and seeing the average, play again a large number of times and see the average, play again a large number of times and see the average. We are getting the idea here that as we keep playing and averaging the payoffs, we seem to get something close to $5. But we can and should find the answer much more directly by understanding what it means that the set of values $2, $4, $6, $8 is an ideal data set. That is, that this set of values is already perfectly representative of what occurs in the long run. Why is that important? It means that if we take the average of these numbers, if we simply add up $2 plus $4 plus $6 plus $8 and divide through by how many numbers there are, we will get $5 as the average of these numbers and therefore conclude that in the long run you will on average receive $5 per play of the game. This is very useful. We don't need actually to roll the die a huge number of times and average the results. Instead, we just perform this computation, and this already knows about the long-run behavior of the experiment. That's what's so useful about an ideal data set. There are actually two different long-term average values that we could ask about in this setting. We could ask, what is the long-term average payoff per play of the game? We already computed that just now to be $5. But we could also ask, what is the long-term average of the numbers appearing on the die? In other words, we're not asking here about the payoffs $2, $4, $6, $8. Rather, we're asking about 1, 2, 3, or 4, the numbers themselves that appear on the die. We could roll many times, look at the numbers that appear, and ask, what's the average of those numbers? The thinking is very much the same here. We have an ideal data set of these numbers. They occur equally frequently because the die is fair, and their long-term average is just the result of averaging up the ideal data set, and that's 2.5. In the long run, as we perform the experiment many times and average the number that appears on the die, on average, we will obtain 2.5. And notice that 2.5, this average, is not one of the numbers themselves. You can't roll the die and obtain, in one roll, a 2.5. There is no such thing. So this 2.5 is an average of numbers that appear over many rolls. We've made here a little bit of a subtle distinction between the two questions we could ask about long-term averages. We'll practice this more in a little while. Now let's make the game more realistic by introducing the risk of losing money. Suppose that it costs a certain amount of money each time you play the game. So far you've just had money coming in over and over. That sounds like a good deal. But to make it more realistic, let's say that it costs you money every time you play the game. In particular, let's say that it costs you $4.75. In the long run, we can ask, what is the average net gain or net loss per play of the game? There are two ways to think about this. If on average you receive $5 per play of the game, just from the money receiving aspect of the game, and you are already definitely paying out $4.75 per play of the game, then overall you have an average net gain of 25 cents, a quarter of a dollar. This is a perfectly good way to compute the answer to the question of the average net gain or loss per play of the game. But there is another approach well worth understanding, and you should be able to do this computation as well. You could write out an ideal data set of net gains and losses. In a perfectly representative 4 plays of the game, you will roll a 1 once, and the result will be a net loss of $2.75. Why a net loss of $2.75? If you roll a 1, then you're bringing in $2 from the payoff itself. But then you're paying out $4.75 for the privilege of paying the game. The net gain or loss is a loss of $2.75. Similarly, if you roll a 2, you'll bring in $4 but pay out $4.75. That means that you are, in the end, losing 75 cents. Similarly, rolling a 3 brings in a net gain of $1.25. Now you're bringing in more than the cost of playing. And finally, if you are fortunate enough to roll a 4, you're bringing in $8 but paying out $4.75, a net gain of 3 1/4. So this too is a collection of numerical values associated with this game, and each one occurs equally frequently when you play the game many times. Having written out this ideal data set of net gains and losses, the average of this perfectly representative set of net gains and losses will give you the average long-run gain or loss. Averaging up these numbers produces a net gain of 25 cents, just as we had computed earlier. Either approach works equally well. The first one is usually easier to carry out, but you really should understand this method and be able to carry it out also. Why is this computation important? We've just figured out that although we could win or lose on any one play of the game, in the long run this game is a winning proposition. The computation tells us something. It gives us useful information about whether it is a good idea to play the game or not. In other words, it helps us make a decision. Should we play or should we not play? Because of its importance in making informed decisions, this notion of the long-term average value of an experiment is perhaps the single most important idea in the entire subject of probability. This is why we are discussing it so close to the beginning of the course, and why we will return to it a number of times rather than just treating it as one topic among many. Now let's make life a bit more interesting. What if the 4-sided die is not fair? We're still playing the same game, rolling a 4-sided die. It's still the case that the dollar payoff is twice as much as the number that appears on the die, but now the die is weighted more heavily towards the low values. There's a 1/3 probability of rolling a 1, still a 1/4 probability of rolling a 2, still a 1/4 probability of rolling a 3, but now only a 1/6 probability of rolling a 4. Before going on to the next video, answer the following questions, and you will probably find them to be a little more involved than previous ones. What is an ideal data set of outcomes of rolling the die and just observing the number? What is an ideal data set of payoffs of the game? What's an ideal data set of the dollar amounts that show up when we use this die? And in the long run, what is the average payoff per play of the game?